Oh, I'm sorry. I didn't know you had any company.
That's okay. Bert, this is Howard and Rajesh. Guys, this is Bert.
Hey, good to see you.
Anyway, I wanted to show you this tourmalinated quartz that we got in the lab.
This is so pretty. Bert works for the geology department.
Yeah. You know what geologists and Bon Jovi have in common?
You're both into rock?
Yeah. Well, see ya. Thanks for coming to the Mineral and Rock Show with me.
We're sorry Amy didn't want to go.
Who needs her when I have you guys? Rock show! Rock show! Rock show! Rock show! Rock show! Rock show! Rock show!
Hello, hello, hello. Welcome to Astronomy on Tap number 73. I am Rebecca Larson. I am your co-host this evening, otherwise known as Chaos Cloud. And with me tonight is...
Hello, I am Micaela Bagley, also known as Deep Space Shine.
We are excited to have the geophysics department here at UT taking over our show. We've got some pretty cool talks for you. So tonight, we're going to have a really fun show about radar sounding. So we can actually look inside planets and moons from space using radars. So Dr. Kirk, like the captain, Scanlan is going to be telling us about that.
And then after our amazing news, astronomy in the news segment, Dr. Chris "The Rock" Lowry will tell us about the recovery of life after the end Cretaceous mass extinction. Super apologies for my words.
Words are really complicated. So science is always better with beer or whatever it is that you are drinking. I currently have one of our really cool koozies with a black hole image, which you'll hear a little bit more exciting news about later. So please go ahead and get yourself comfortable, grab a drink, whatever you are having. We want to give a shout out to the North Door. It was our venue for over 5 years. Unfortunately, given the circumstances, they had to shut down. And so please, if you have any good memories or things that happened at the North Door, go ahead and tag them. Let them know how much that it meant to us and to you to be at the North Door for the past so many years, every month for Astronomy on Tap or any other events that you might have done there.
We will be celebrating the North Door for a long time. That was a really
This is not getting off of our slides at any time. Dude. Also, special shout out to the Austin Astronomical Society for being one of our sponsors. We appreciate you coming to every single one of our shows and for being the enthusiastic astronomy people that we really cater to here at Astronomy on Tap.
So during the show, before the show, after the show, all the time, connect with us on social media. We are on YouTube. You have found us. We also have all of our previous shows are up there for you to check out on our YouTube channel. Check us out on Facebook, Twitter, Instagram. You can email us and you can check out our relatively new website, AoTATX.org. Or you can check out Astronomy on Tap headquarters, which has information about all of the Astronomy on Taps that are happening all around the world at astronomyontap.org. So lots of astronomy virtually in these times to enjoy from your living room.
Yeah, so also want to give a special mention to all of the Astronomy on Tap locations that are doing virtual shows. If you go ahead and check out this YouTube channel and look at the ones that we follow, you'll see many other different locations for Astronomy on Tap are doing live streams. In fact, I believe even our neighbors in College Station, Texas are doing their show tomorrow night. So go ahead, if you enjoy the show or if you keep wanting to learn about astronomy, there's lots of things that even just our organization, Astronomy on Tap, is doing globally. So check that out, and we will try to share those as much as possible, especially on Twitter, where we are as active as we can be. So we are on Twitter at AoTATX, and if you use the hashtag AoTATX73, you can ask us questions there. You can ask us questions in the YouTube comments. We do have people moderating those and passing those along. So while the speakers are talking, as soon as you have a question, go ahead and send that to us. Since there is a bit of a delay, we'll get those in time to ask the speaker after they're done with their talk, or if you have questions during the news, same thing. We will do our best to answer as many as possible, and so go ahead and just throw all those questions at us that you can, and we will get through them.
We are still doing trivia. We have a little bit of an abbreviated game for you today. It's short, but that means it's even easier to win. So check out trivia. There's a link here and a link in the video description. And pay attention to the talks. The questions will be answered during one of the talks. I'm not going to tell you which one. We are still choosing trivia winners. And if you have been a trivia winner in the past and you have not yet received your prize, don't worry. We haven't forgotten about you. We have a plan. I know you've heard that before, but it's real this time. And I'd also like to mention that you do not have to get all of the answers correct to win. We choose winners from among people who get all the answers right, and we choose a winner at random. So you don't have to get everything right to win a prize. Play our trivia game.
Yes, so we have cool prizes. Some of them, it might be random what you get, but we also have these really cool coffee mugs that Odell Brewing Company, one of our sponsors, has made for us. And we have some coasters that
here's the coaster that we have to match the mug. I don't know if you can see that.
We also have some other things that we might be sending you. So when we figure out how to go to the post office, we will be doing that. All right, so please be kind to each other, be respectful. Even though we are on the internet, please be kind to each other. It is a no harassment zone. We do have people moderating the comments. We will not tolerate anybody being abusive or condescending or anything like that to anyone in our show. Or to our speakers. Please, this is a show to learn and to connect with other people, and please use that time wisely. So without further ado, before we launch into the show for this week or this month, I want to mention to all of our audience who tuned in last month or wanted to, we had our show in Spanish, and it was awesome and so exciting. We had the entire show in Spanish with guest hosts and guest news anchors, and it was a really, really awesome, exciting show. And we just want to encourage all of our non-Spanish speaking audience to check out that show on YouTube. You can find English subtitles in the closed caption option, and they do a decent job. So you'll get a really close, good translation. It's not perfect, but it's a little fun to follow along there. So we encourage everyone to check that out. There were some really great talks during that show. And if you missed them, they're all there on YouTube. Yes, very important. Thank you for mentioning that. All right, so let's get started. If we could have Dr. Kirk Scanlan join us. Hello, welcome. So Kirk is currently a postdoctoral fellow at the University of Texas Institute for Geophysics, or UTIG. Dr. Scanlan uses radar measurements to interrogate the subsurface and inform problems across a variety of disciplines, including civil engineering, glaciology, and planetary science. He's a member of the Europa Clipper science team, who are working together to use NASA's Europa Clipper spacecraft to evaluate the habitability of Jupiter's moon, Europa. In his spare time, he enjoys yoga, running, and rock climbing, as well as spending time with his dog and his fiance. So Kirk, if you could go ahead and take it away. Thank you.
Great. So good evening, everybody. I'd like to thank the organizers for allowing me to give this talk tonight. And as mentioned, I'm a postdoc at the University of Texas Institute for Geophysics here in Austin. And I'm going to talk tonight about what I think are some of the most amazing instruments humanity has ever put in orbit around another planet or moon. And those are the radar sounders. And even though I may be a little biased, I think it's very true. So to start, I'm just going to give a brief introduction to what radar sounding is. Slide is not advancing for some reason. Do it this way. There we go. So what is radar sounding? Radar sounding is essentially the transmission and reflection of electromagnetic waves. When you start getting to around megahertz frequencies, these electromagnetic waves can penetrate most naturally occurring materials, so rocks, soils, and ice. So essentially what we're doing is what we see here on the left. We have our spacecraft in orbit around some body, sending out electromagnetic waves that are propagating. They hit the surface, they go through, hit another surface, keep going through, getting progressively weaker. At the same time, whenever those radar waves contact an interface between materials with different electromagnetic properties, it generates a reflection. So when it hits that surface, part of that wave gets reflected back. Part of that transmitted wave gets reflected back. And if we can measure those reflected waves, we can start to build an image of the subsurface beneath our spacecraft. And by repeating this image along an orbit, we generate a two-dimensional image, and then we can look inside different planets and moons. So I'm just going to go over quickly some of the different radar sounders that have been put in space, what bodies they've targeted, and a little bit about what's coming down the pipeline in the future. So probably the most obvious target is Earth's moon. It's been visited by a couple different radar instruments. The Japanese Space Agency has their Cayuga spacecraft. It carries the Lunar Radar Sounding Experiment. The antenna is this big, long thing sticking out the side. NASA's Apollo 17 mission had the Apollo Lunar Radar Sounder Experiment. Its antenna is right here. We have 2 spacecraft in orbit around Mars currently that carry radar sounders. NASA's Mars Reconnaissance Orbiter carries the Shallow Radar, or SHARAD. And ESA's Mars Express spacecraft carries the Mars Advanced Sounder for subsurface and ionospheric sounding, or the MARSIS instrument. What's really interesting about SHARAD and MARSIS is that even though they've been there for a decade and a half, like MRO arrived in Mars in 2006, both of these instruments are still collecting data today. So even though it arrived when I was in high school, there is still data that's coming down, new measurements of Mars that are still being made today. And sorry, I just had a window pop up in front of my other window. And what's really interesting is all this data from Mars is freely available online. So if you go to this website right here, this will take you to the Mars orbiting data analysis node of the NASA planetary data system. And you can go through and look at all these fantastic pictures of Mars. And I'll show some a little bit later. Coming down the pipeline, we also have 2 missions to Jupiter's icy moons that carry radar sounders. So we have NASA's Europa Clipper spacecraft, which carries the Reason instrument. I'll talk more about that later. And ESA has its JUICE spacecraft, which carries the RHIME radar sounder. Europa Clipper is specifically going to look at Europa, and JUICE is going to visit Europa, Ganymede, and Callisto. And then finally, just because it's really interesting and I find it really cool, I've included the Cassini spacecraft and its radar altimeter as a radar sounder, even though it wasn't designed to be a radar sounder. And it's really interesting because when they started doing flybys of Titan, they realized using the radar altimeter, they could start seeing through the methane lakes on the surface of Titan. So we actually have bathymetry measurements of methane lakes on Titan with the radar. And I think that's just fascinating. So these are just a sample of kind of the different radar sounders that have been used in space and kind of the different targets we've looked at across the solar system. And now I want to take a look at just some existing data, and then we'll talk a little bit more about Europa Clipper in specifics. So this is just some, I'm going to look at existing data from Mars. And we're specifically going to look at the polar layer deposits in the North and South Pole. So this on the left is an image of the Martian northern polar cap. And I've pulled out a section of SHARAD orbit 5192, and the ground track is shown here on the left. So what you see is this is a 2-dimensional image of the inside of the Martian polar caps. Just to orient, we have the Martian atmosphere at the top of the radargram. It intersects with rock below. But when you're going over the polar caps, you can actually see through the ice to the rock below. And to give a sense of scale, the northern polar caps are approximately 1,500 kilometers long and 3 kilometers thick. So we're really seeing a lot of fine scale structure within the northern polar layer deposits of Mars. And you see all these beautiful internal layers that are super clear in the radar. And what these actually are, these are dust layers that when that part of the northern polar cap was exposed to the surface of Mars, some dust accumulated and then was covered in ice again. So what we're actually looking at with these internal layers is the complete climactic history of Mars preserved in the northern polar layer deposits. And that's something we can interrogate and study with the radar. And also interesting is where these layers start intersecting or outcropping at the surface, we can match that up with camera images using the context camera or a high-rise imaging system to actually see those layers on the surface and be able and really fine detail and to track them back into the ice. It's really, really interesting, or at least I think so. And because the Mars Reconnaissance Orbiter is in a polar orbit and it's been operating for 14 years, we have a lot of data over the northern and southern poles of Mars. So that allows us to construct these three-dimensional models of what the northern and southern polar layer deposits look like. So that's what's shown here is just a three-dimensional cutout. So you can see all this fine scale layering. We can study how it moves, how it differs all the way through the northern polar caps. We can see buried craters, buried structures within the ice that we won't be able to see from just a single two-dimensional image. And we can do the same thing with the southern polar cap. So this is now the south pole of Mars. You can see the polar cap there, and we can build these three-dimensional structures again. Now, what's really interesting is that the south polar cap of Mars looks much different than the north polar cap. We don't see much of that really fine scale layering that we saw in the northern polar cap. We can still see some buried craters. You can see some CO2 ice deposits on top of the more water ice rich polar cap. And it's still an outstanding question why the southern polar cap appears so different in radar images compared to the North Pole. And it's something people are actively working on right now. So now I'm going to leave Mars behind and take a little bit more of a look into the future and where radar sounding is going. So for anybody who doesn't know, this is Europa, or this is an image of Europa. Europa is the second Galilean moon of Jupiter, first observed in 1610. It was the least studied Galilean moon by Voyager 1 and 2. But we knew from images that it was really bright. And that was always puzzling, like, why is it so bright? Because usually you expect things to be dull that have been in space for a long time. But it was a primary target of the first Galileo extended mission. And what Galileo discovered, in addition to these really, really beautiful images, is that Europa has a putative global ocean that contains 2 times all water on Earth, all the water in Earth's oceans. So if we add up all the water in Earth's oceans and double that, that's how much water is in this global ocean on Europa. And you can see it here, kind of this in this cutout. We have a iron core, rocky mantle, then this thick ocean underneath an ice shell. And what's also interesting about Europa is if we look in the image in the background, you notice there are almost no craters on the surface of Europa. If you think of our moon, it's just covered in craters. And because Europa has no craters, or very little craters, that suggests that there's an active resurfacing going on Europa. So from a habitability perspective, there's a lot of active processes going on Europa that are able to move different chemicals around the system into the ice. And that's really interesting from a habitability perspective. So to that end comes Europa Clipper. And Europa Clipper is going to Europa with the specific goal of determining whether Europa could harbor conditions suitable for life. So we are very much a habitability focused mission. Europa Clipper is scheduled for launch in 2024. It's supposed to arrive in Jupiter sometime 2030, 2031. We have a 4-year science phase when we're actually orbiting Jupiter, but doing approximately 50 or so flybys of Europa. Europa Clipper has 9 different science instruments. So we have a camera, magnetometers, a whole range of spectrometers, and then our radar sounder. This is the Europa Clipper mission patch on the right. And I'd very much suggest anybody who wants a little bit more information on Europa Clipper, check out the Europa Clipper webpage. There's a lot of interesting videos and animations and a lot of interesting information about Europa Clipper and why Europa is so exciting. So this is the Europa Clipper spacecraft. It's somewhat of an old image. Not much has changed, more just the positioning of our radar antennas that you can see here hanging from the solar panel. So we have the main bus in the middle, high gain antenna, the mag boom. We We have our solar panels, and then the radar sounding antennas hang off the bottom of the solar panels. It's quite a big spacecraft, end to end on the solar panels. It's about 25 meters long, so it's quite big, and it's quite an impressive spacecraft when it'll actually be built. And what's interesting about Europa Clipper, and if you may have already noticed, you may not have, but up here in the top left corner of the mission patch is actually the University of Texas Institute for Geophysics. So UTIG in Austin is represented right on the mission patch, and that's because UTIG is home to the radar sounder, which is called REASON. REASON is the radar for Europa assessment and sounding ocean to near surface. So it's quite a mouthful, but we just call it REASON. REASON has 5 main science objectives, which I've listed here. The first is to really investigate Europa's subsurface ocean. So using the radar sounder, can we get down and through that ice shell and actually image that ice ocean interface? Estimates for the thickness of the ice shell range from 3 kilometers, which is kind of similar to the Martian polar caps, to 30 kilometers, which is much thicker. If we can image that ocean, then we can measure the ice shell thickness. Even if we can't measure the ocean, we can put a constraint on the thickness of the ice shell. We can look at improving our understanding of the ice shell structure, because how the structure of the ice shell, how it changes, has important implications for the habitability, how different chemicals are different of the chemistry required to support life moves from the surface into the ocean, and all that is dependent on how the structure in the ice shell moves. Is it convecting? Is it conductive? Are there diapirs? Are there cracks? And that's something we're going to get at with REASON. We're also going to study the elevation, composition, and roughness of Europa's surface. And then one thing that's kind of not super obvious that you can do with the radar sounder, but really interesting, is we're actually going to search Europa's atmosphere for indications of plumes. So if Europa is anything like Ganymede and the tiger stripes on the south pole of Ganymede, which is Ganymede's a moon of Saturn, there it's hypothesized that those plumes are in direct contact with the ocean. So if you can image them and study them, then you're actually studying the ocean under the ice shell of Ganymede. So maybe that's similar for Europa. We don't know. So REASON is somewhat interesting compared to other radar sounders, is that we have 2 different frequencies. So we have our HF band, which is a lower frequency, which translates to a longer wavelength, and our VHF band, which is a higher frequency, shorter wavelength. This image on the right is the highest resolution image of Europa's surface that has ever been taken. It was taken by Galileo, I think in 1997, either 96 or 97. So I was either 8 or 9 when this image was taken. And you can see the surface is really different in different spots. In the top part, you have some more smoothie, ridged plains. Then you have all these disrupted, kind of darker, more modeled terrains in the middle. The texture of the surface has really important implications for the radar. So we have 2 different frequencies to try and make sure we can get through the surface and see deep, but also maintain our resolution. So our HF band is expected to penetrate deeper than the VHF, just because it is less affected by that small roughness at the surface. The corollary, though, is the VHF, so that higher frequency, shorter wavelength band, is expected to provide better depth resolution. So any fine scale structures like those layers we saw in the North Polar layer deposits on Mars that may exist within the ice shell of Europa, there will be better imaged in our high frequency band than the low frequency band. And then it's the combination of both that allows us to study Europa's ionosphere. So that is it for me. Thank you all for listening. And if there are any questions, I will try my best to answer them. Thanks.
Awesome. Thank you, Kirk. Thank you for that awesome talk. I certainly learned a lot. I hope our audience did as well. We have a few questions coming in here. And so give me a second there's a little bit of a delay between us and the YouTube, so they're going to be coming in later. But to start off, here's a question. What can the 3D maps of the Mars polar caps tell us about the planet's history? And there's a second part to that, which is essentially asking about if we can learn anything about the planet's habitability now or in the past.
That's a really good question. And so we know there are different layers or there are different stages to the northern polar cap of Mars. That was work that was done at UTIG by a former PhD student. So we can tell a little bit about how Mars evolved by just looking at how the northern polar cap grew over time and kind of the different structures. If we see some large scale dipping in the internal layers, that might be indicative of maybe some preferential erosion in one area versus the other, which tells us a little bit about the winds. But yeah, it's not directly my field of expertise, and how that translates to current habitability. Yeah, that is far beyond me. So
it was cool. It was really cool to see like how much level of detail we already know about the Mars polar caps. At least to me, that was really exciting. Okay, we have a question from Brad, who's asking, when is the Europa Clipper due to set off, and how long until it's in place around Europa?
So the scheduled launch date is 2024, and it'll take about probably around 6 years to get there. There's still a little bit of uncertainty as to how Europa Clipper will get there as with the launch vehicle, but it'll take, I think it's currently up to 6 years to get there. So it'll be 2030 before it gets there. Has to do maybe a year or so of pump down to actually get into stable orbit, and then it'll start doing data collection. Okay, so a fair way to go yet.
Okay, does the 6 years include the slowing down into stable orbit part?
I don't believe so.
Okay, cool. So stay tuned, everybody.
Yeah, the Europa Clipper is a flagship mission, so they take about 30 years by the time they actually do the proposal till it actually gets there. So there's be a whole generation of new scientists that will have to come on and deal with it.
Nice, and right, and benefit from all of your hard work.
Yeah.
We've got another question. How much power do radio sounding instruments use? Is this an issue in the outer solar system?
So Reason will be the strongest VHF transmitter outside the asteroid belt when it gets there. But it's still, we're limited to what we can fit on a spacecraft. So when we do radar sounding on Earth for glaciers and ice caps, we have a lot more power than we do on the spacecraft. So there are ways to get around it. We use chirps. So it's like a big long whistle. Like if you were to whistle from like a low tone to a high tone, that's kind of like what the signals look like. So if you stretch that out, you can fit more power into a longer chirp. That it has some issues later on, but yeah, it is power constrained.
Okay, nice. Let's see. We have a couple more questions, it looks like, but I think we'll move on for now. And if you're able to stick around, we'll do we'll bring you back at the end of the show for a little bit of a panel question and answer discussion, if that works for you.
Sure.
Awesome. All right, cool. Thank you very much for that talk and for joining us today. All right, and so now we are going to move on to our Astronomy in the News segment, and we've got today we have Oscar and Sam who are going to be telling us all about what happened over the last month. So, there we go. Hey guys, all right, take it away.
All right, sweet. I'm just gonna share my screen real quick. All right, here we go.
No sound. Imagine very bombastic music.
The vastness of the universe. All right, sweet. So, what is going on, everybody? Hope you're all having a wonderful day today. My name is Oscar, but I'm known here as Señor Galáctico, and I will be co-hosting Astronomy in the News tonight alongside Sam, otherwise known as MCMC Hammer. We're going to start off the news with a pretty cool NASA mission. So take it away, MCMC Hammer.
Yeah, so this literally happened, 2.5 hours ago. The OSIRIS-REx mission, which stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. And if that isn't a mouthful of a name, I don't know what is. So the OSIRIS-REx mission touched down on the asteroid Bennu, again, as I said, literally 2.5 hours ago, and collected a sample of the regolith, the soil, the pebbles, some material from a asteroid. And when it gets back, scientists are hoping to analyze it and learn about the formation and evolution of our solar system. The asteroid that it visited is one of the oldest kind of fossils of the formation of our solar system. So we can learn about that. We also know that these asteroids and comets are a potential source for organic compounds that were deposited on a very young Earth and then led to the formation of life here. So just going through the approach sequence, you can kind of see there's an animation in the top left here. This is actually real imagery taken from a touch and go dress rehearsal that happened, I believe it was in April. So these are real images from the surface of Bennu that will look almost exactly like what we see when we actually get the images from the most recent touchdown. So it comes down, it reaches out with this arm and touches it with what's called the TAG SAM, the Touch and Go Sampler instrument, which you can see in animation at the bottom here. And basically you want to use a vacuum, but you can't really do that in space because you're already surrounded by nothing. So there's nothing to suck up. So what they do is they actually blow gas around the kind of edge of this sampler head. It scoops up material and then deposits it into a little filter kind of thing on the edge. And then as soon as the spacecraft detects that it's touched, it fires off these gas bottles and then backs up to safety. And so we have confirmation that all of this happened. We actually got some material. We don't know how much yet. And that's going to be determined over the next couple of weeks, probably. What they're going to do is you don't really have a scale in space. So they spin this sample collection instrument is on a big long arm. So they're going to spin up the spacecraft and measure the difference in where the center of mass is before they took the sample and after they took the sample. And that's going to tell them how much they actually collected. And they're looking to get about 60 grams or 2 ounces of material, which is about the mass of a C-sized battery. So not that much, but it's going to tell us a lot about the early solar system. So go check out the NASA TV. I'm sure you can find a rebroadcast of it. It was a really exciting event that happened just a few hours ago. So now from something a little closer to home, this asteroid, to black holes.
Black holes.
Way far away.
Very far. Yeah, but thanks, MCMC Hammer. That was actually super, super cool news. NASA doing cool things yet again. But yeah, kind of transitioning to more, galactic scales. We're kind of going more into like this recent news that a black hole, like there's now evidence that a star has been kind of ingested inside of a black hole. So the team using the ESO, which stands for the European Space Observatory Telescope, they found evidence of a black hole eating a star like spaghetti. This black hole is located 215 million light years from Earth, and the black hole has a mass roughly 1 million times that of our own sun. The unlucky star that was eaten was about the same mass as our own sun, so really this star stood no chance against the gravity imparted by the million solar mass black hole. The concept of spaghettification is not something new. Scientists realize that the tidal forces near a black hole is so strong and sharp that objects that are unlucky enough to fall in will be stretched and pulled and ultimately become spaghettified. However, until now, this was just merely theoretical speculation. What is new is that this is the first observation of this tidal disruption actually happening to a star. So the team didn't actually observe the star fall in and see that trail like you saw in the animation. What they saw was more like the flare being ejected by the black hole, which is what would happen if a star were to pass within the event horizon and get eaten up by a black hole. Another thing that makes this kind of newsworthy is that usually these types of events are obscured by dust and gas, and it blocks the view of the astronomer. But this one was one where they were able to see the flare clearly and make some measurements that corroborates the hypothesis of a star being eaten up and spaghettified by the black hole. So this is like really, really cool stuff, and really a time to be alive, really. So now we're going to move back to more terrestrial news and turn our attention to our planetary neighbor, Mars.
Yeah, so this is kind of a interesting coincidence that we have this science in the news this month, and we also have the Geoscience Takeover of AoT. This actually was a study that used some of the instruments that we just heard about. So if you remember back in 2018, I think it was, there was big news about a lake that had been discovered on Mars. Well, this is more evidence that this lake is actually there. So a team of astronomers in Italy, or not necessarily astronomers, planetary scientists in Italy, used the European Space Agency's Mars Express Orbiter, and specifically the MARSIS instrument, which we just heard about, the Mars Radar for Subsurface and Ionospheric Sounding instrument, to go back, and they analyzed some of the data that was used to produce that 2018 study, but also some new data. And really interestingly, they analyzed it in a new way that was actually developed back here on Earth to find subsurface lakes under the Greenland ice sheets. So they had used this radar sounding technique in Antarctica to find lakes, but it didn't work so well in Greenland. So they needed to come up with a new technique. And what they did is, and I'm sure Kirk can explain this better than I can, and can definitely answer your questions at the end. But instead of just looking at essentially the brightness of the radar reflection, they also looked at how smooth the surface that it was reflecting off of. And as you would expect, lakes like to form in nice smooth surfaces, whereas these dust layers that they were finding are much more rugged. So this new lake that they found is about 20 kilometers wide, or about 12 miles, and it's surrounded by some smaller patches of liquid water. It's likely extremely, extremely salty water. The temperature of that region is about minus 190 degrees Fahrenheit. So as you would expect water to freeze at 32 degrees Fahrenheit, something is keeping it liquid, and that's most likely that it's just very salty. And this lake could possibly harbor life. I don't want to make any statements more than possibly. There are some extremophiles here on Earth that live in cold, salty water, not nearly as salty as this water would need to be to maintain its liquid state. But unfortunately, it's also buried under about 4,000 feet of ice. So it's going to be very difficult to actually get down there and sample the water and see what's going on. So again, possibilities, a possible sanctuary for something to be growing down there. Absolutely no evidence that there is something there, though. And now we'll go back to black holes. This is lots of black hole news.
A lot of black hole news happened, yeah.
And big news on this one.
Big news, yes. So as probably most of y'all heard, the Nobel Prize in physics has been announced. So the Royal Swedish Academy of Sciences just announced this year's winners. They awarded it to 3 people. Dr. Andrea Ghez and Dr. Richard Genzel share one half of the prize for their groundbreaking work in showing evidence that a black hole resides at the center of our own Milky Way galaxy. The way they found this evidence is kind of like the video showed is they mapped out trajectories of stars near the center of the Milky Way. Let me see if I could replay it. Okay, sweet. The star, this one here, you can see that it kind of goes down and then does like a really quick wraparound, and then this like highlighted star here is kind of where the team believes the black hole to be. And so using some kinematics and some physics, Kepler's third law, they kind of calculated an estimated mass for what this invisible entity should be that's causing the orbit to act the way it is. And they found that it's something close to like 2.6 million times more massive than the sun. And so basically, if you see something not there, nothing luminous, but it's able to have that strong of a gravitational pull, and the math turns out that it gives us like something like 2.6 million times the mass of the sun. The really only conclusion is that there has to be a supermassive black hole at the center of our Milky Way galaxy. And this is a truly remarkable achievement for both, and even more remarkable for like the UC system. The 2 UCs really out here representing, and honestly, I cannot give the news without giving my undergrad institution a shout out. So go Bears, yo. The other half of the prize was given to Dr. Roger Penrose, who showed that black holes are consistent with general relativity and are indeed possible. So the mathematics to prove this was extremely difficult, and it was not until Penrose came along to tackle this problem that he uncovered kind of more mathematical tools we can use to apply to general relativity in the extreme regimes of black holes. So typically what has been done before was you make these approximations to make the problem a little bit easier to solve. In physics, there's a kind of like a running joke is like the spherical cow approximation. And the concept of that is kind of simple. So you turn a complex problem into a very easy problem that allows you to solve it. But it has its little drawbacks as it's not able to reflect the true nature of the original problem that you set out to solve. But what Penrose showed in his paper that he won the Nobel Prize for was kind of that no matter what the approximation you do to the black hole, when you do the math and plug it into Einstein's equations, it's consistent. You're still able to form a black hole regardless. And so this is just further confirmation that one, black holes do exist and are consistent with our theory of general relativity and how gravity works in these regimes. Okay. Then Sam, take it away.
Yeah, so that is it for the news for this month. Thanks for coming out. Again, ask your questions in the chat. I think we'll be back on at the end to answer them. And don't forget to vote.
Please vote.
Nice. Thank you, Oscar. Thank you, Sam. That was an exciting set of news stories. A lot went on this month.
It did.
Yeah.
And
Exciting
today.
times.
This was like a well-timed show.
Absolutely.
Nice. All right. Well, thank you. Yeah, stick around and as Sam said, don't forget to ask your questions in the chat for the news stories too, because we'll bring everybody back at the end and answer all your questions that you have. So definitely keep adding those. All right. Thank you, Sam and Oscar. And we are now going to move on to our final speaker. So Chris, can you join me with your excellent hi? So Chris Lowry is I'm going to get all of this wrong, a paleoceanographer specializing in micropaleontology, and is a research associate at the University of Texas Institute for Geophysics. And your job title there includes like all of my favorite words when I was a child. And I bet that's true of a lot of people watching today. So that's really exciting.
Yeah, and the topic of my research covers all of my favorite topics as a child. So yeah, it's good.
Nice. It's good when that works out.
Yeah.
So, take it away.
All right, yeah, let me just share my screen here. And yeah, all right, so thank you guys all for sticking around. My topic is the recovery of life after the in-Cretaceous mass extinction, so bringing our topic back down to Earth. The in-Cretaceous mass extinction, of course, was caused by the impact of an asteroid in the Yucatan Peninsula. It's the only major mass extinction in Earth history that was caused by an asteroid. And it was something that we went out and drilled the crater as part of an expedition back in 2016 with the International Ocean Discovery Program. Took cores within the crater to understand how life recovered there. So before we get started, I want to just briefly acknowledge my co-authors, and particularly Andy Frost, Heather Jones, Tim Braylauer, and the entire IODP Expedition 364 Science Party. A lot of people contributed to this expedition and the science that has come out of it. And it's really cool. These things are always really multidisciplinary, but you know, to be a paleontologist working alongside impact petrographers and people that study, you know, the effects of soot in the atmosphere and things like that, it was just a whole lot of fun. So why do we study mass extinctions in the first place? Well, we may or may not be living through one today. You probably are familiar with the term the sixth extinction. So there are 5 canonical mass extinctions in Earth history, going back the last 500 million years. The in-Cretaceous, of course, is the most recent one. But the Earth system has been changing a lot since humans have evolved and have become dominant on the planet. This is a figure that I think always blows my mind when I look at it. This is vertebrate biomass on land. So terrestrial vertebrates, so like elephants and pigs and cows and rhinoceros and woolly mammoths and whatever. This is 10,000 years ago at the end of the last ice age. You can see this is vertebrate biomass on land. And then in 2015, this is vertebrate biomass on land, several times higher than you know, the end of the last ice age. And it is almost all people and domesticated animals that we eat. And wild vertebrates are extremely, extremely low compared to what they used to be. And there's tons of, you know, facts and figures we could throw out here, but some examples. 800 animal and plant extinctions have been observed since the year 1500. And that's just observed. You know, our knowledge of the diversity of life on Earth is very incomplete. And there have definitely been a lot of species that have gone extinct without ever having been described. There are currently, again, of things that we even know about described species, there are 17,000 species that are categorized as threatened, according to the International Union for the Conservation of Nature. Wild terrestrial vertebrate biomass has declined 60% just since 1970. So in the last 50 years, it's dropped more than half. And modern extinction rates, so the number of species going extinct every year, are between 10 and 10,000 times higher than background natural, quote unquote, natural extinction rates. This is a figure from a paper I really like by Payne et al. On Science from a few years ago. It looks at extinction in the oceans going back the last 66 million years. So over here on the left, this is the in-Cretaceous mass extinction. These little green fish are marine vertebrates, and these little blue shells are mollusks. So, you know, oysters and clams and gastropods and all that. So what we see here is, you know, the in-Cretaceous mass extinction, we see between 40 and 50% genus extinction. So species, right, is like the highest level of organization, and the next one above that is genus. So 50% genus extinction at the in-Cretaceous. And then for the last 66 million years, extinction rates have been low, right? Around, you know, less than 10%. One little bump here at the end of the Eocene, but otherwise very low. But then if we look at what's going on today, if we make some assumptions about everything that's currently threatened, and again, because we don't, first of all, we don't know how many species there actually are, because we haven't described every species on Earth, we're not even close. Second, we don't have a good understanding of how many species actually are threatened. We know the big charismatic ones like the white rhinoceros or the vaquita that lives in the Gulf of Mexico, the Gulf of California, manatees, things like that. Like, we know that the big charismatic things are threatened, but we don't know all the other little stuff, how much of that is threatened as well. But if we look at just the things that we know are threatened, we make some assumptions extrapolating it out to everything else that exists. We are looking at between 30 and 40% genus level extinction if everything that's currently threatened eventually goes extinct. If that happens, we're right back to in-Cretaceous levels of extinction, and we definitely would be living through a so-called sixth extinction event. Obviously, we want to prevent that, and I want to emphasize that this hasn't happened yet. And whether this happens or not will depend entirely on the choices that we make as a society over the next couple decades to stop climate change, stop overfishing and overhunting and pollution and habitat destruction and all the other stuff. We can still prevent all of this. But if we don't, this is what's going to happen. And it's really important then that we understand how extinctions work, and we understand how organisms recover from extinctions, how the biosphere recovers from extinctions. So to do that, we want to look at the in Cretaceous, which is the most recent mass extinction in Earth history. Here's a famous in Cretaceous boundary section called the KPG boundary. We have a lot of geologic, ages. C was already taken for Cambrian and Carboniferous, so they had to use K for Cretaceous, just in case you're ever wondering. This is the Cretaceous Paleogene boundary. This is Gubbio Gorge in Italy. These rocks down here are Cretaceous. These rocks up here are Paleogene. So dinosaurs, no dinosaurs. But these are marine rocks. You might notice there's no dinosaur bones or like mosasaur bones or whatever sticking out of these rocks. Most of the time you find those big charismatic things very rarely. You got to go to an outcrop and really look around to find like a T-Rex bone. But marine rocks are filled with microfossils. They're literally, limestone is just literally built of microfossils, including the group that I study, which are called foraminifera. These are some Cretaceous forams. They were all big, diverse, weird looking. It was a really great time to be a foram. And you find these things in these rocks down here in the Cretaceous all the way up to this last layer of limestone. And then there's a little clay layer. And above that, there is a big extinction. Almost all the species are gone. There's just a few survivors. 95% of plankton forams went extinct at this level. And they're a lot smaller, they're less diverse, and that starts right here. So it wasn't a gradual extinction event. It was really, really fast. For a long time, geologists didn't know why it was really fast. So these two guys came along in the very late 70s, early 80s. They published a paper in 1980. This is Walter and Louis Alvarez, who were a father and son team of geologists and a physicist. And they were studying the in Cretaceous mass extinction and the Cretaceous Paleogene boundary. And they were thinking, okay, well, if there's a really rapid extinction event, why was it so fast? Maybe what's going on here, they thought, was maybe there was some time missing. So maybe it wasn't actually really fast. Maybe there was just time missing from this rock, and there weren't any rocks deposited in between these two limestones. That's why there's this clay layer here. So to figure out how much time might have been missing, they measured an element called iridium. Iridium is not found naturally in the Earth's crust, but it is very common in space rocks, asteroids, meteorites, things like that. So every time like a shooting star shoots in the atmosphere, every time one little micrometeorite burns up and vaporizes in our atmosphere, it brings in a little bit of iridium. And that little bit of iridium very slowly settles down to the Earth's surface, makes its way into the oceans, and builds up in marine sediments at a very steady rate over time. And we know what that rate is, and we can use that then to calculate how much time has passed if we can figure out how much iridium is in certain rocks. So they studied the amount of iridium that was in these rocks, going from down here to right across this boundary, across the clay layer. And they found background rates. And then at the clay layer, if there was some time missing, they'd expect to see like a little bump and then back in background rates. But what they found instead was a huge spike, 80 times background iridium, which is more than you could possibly explain with millions of years of missing time, which there clearly wasn't. And so they thought, oh, wow, maybe there's an asteroid impact here. And they started looking at it more closely, and they found other evidence of an asteroid impact. They found, ejecta, spherules, microtectites, shocked quartz, these other things that are really typical of asteroid impacts. And they published the hypothesis in the early 80s, which really was a huge deal in the paleontology world, and started a big controversy that lasted until they found a crater in the early 90s. But I don't have enough time to get into the whole story here, but it's really good stuff. Anyway, so this was a really fast extinction event. The asteroid hit, everything would extinct right away. But what's interesting about this is the extinction was really, really fast, but the recovery of life wasn't. So this is a couple plots here of the diversity of two different kinds of marine plankton. I'm going to keep talking about plankton because A, it's what I study, so it's what I know about, but B, because it's in the oceans, which have much better sedimentary records, and they're really small, which means we find them easily in every piece of sediment we take out of a core sample. We have really, really good records of the diversity of marine plankton. way better records than we have of the diversity of different dinosaur groups or whatever. So we can see this at a much higher resolution. What we find is, this is calcareous nanoplankton, which are a type of phytoplankton, plankton foraminifera, which are a type of zooplankton. So phytoplankton, are plants. They produce energy via photosynthesis, and zooplankton eat those things. Anyway, so they increase in diversity, and then at the end Cretaceous level, they have this huge extinction. But then both groups, nanoplankton start to rebound, but it takes them about 10 million years. This x-axis down here is age, million years before present. So about 10 million years before they actually get back to anywhere close to in-Cretaceous levels of diversity. Same thing is true with forams. They have this extinction. They start to come back a little bit, but it's 10 million years before they're back to even mid-Cretaceous levels of diversity. It's a very long time for recovery. And here again are these nice big diverse Cretaceous forams and little tiny undiverse Paleocene forams. So this delay in recovery of diversity is actually something that we see across all fossil groups after all major extinction events. This is a paper by Jim Kirchner and Ann Weil that was published in Nature back in 2000. They looked at each of the so-called Big Five mass extinctions and found a lag between the peak in extinction and the peak in originations that followed when new species are being developed. And with each of those, the lag is about 10 million years between diversity and extinction. And so with other extinction events, you might think, well, okay, sure, like the Permian was like massive volcanoes that were spewing lava out on the Earth's surface for a long time, and it put all these poisonous gases in the atmosphere, and it really screwed up the oceans. It was a long, drawn-out process. The Siberian traps were erupting for millions of years, and so that would explain why the recovery was so slow, because the environment was still being perturbed by these changes. Well, with the in-Cretaceous mass extinction, that's definitely not the case. The asteroid hit, everything went extinct, and then the environment recovered very quickly because it was a very ephemeral climate change event that was caused by this asteroid impact. So to understand this better, we wanted to go look at ground zero of the mass extinction event, which is in the Chicxulub crater. Chicxulub is the name of the crater where the asteroid impact occurred. It took me a while once I started working on this project to learn how to spell it. Fortunately, as a paleontologist, I'm used to learning how to spell things. But anyway, it's down here, in the Yucatan Peninsula in the Gulf of Mexico. Cancun is right over here. Austin, of course, right up here. This part of Texas would have been utterly destroyed by the blast wave and the tsunami that came up afterwards, after the asteroid hit. But we wanted to drill. The crater is currently partially on land and partially offshore, but we wanted to drill offshore because we had better seismic data. We could actually see what we were doing. We wanted to drill this feature of discontinuous hills in the middle of the crater called a peak ring. You can see in the seismic image here, here's the rim of the crater coming in, and there's this little bump here, that's the peak ring. We wanted to drill right here, see what the peak ring was made of. It's a topic for another talk. But anyway, we went offshore and we drilled as part of the International Ocean Discovery Program. It's the most recent version of scientific ocean drilling, something we've been doing as a community for more than 50 years. This is Earth Science's version of like the Hubble Space Telescope or the Europa Clipper. This is how we go out and collect data, collect samples that we would never be able to get otherwise, right? This is big science. This is really major expeditions to go do this stuff. Normally, we'd use this drill ship called the Joides Resolution. Unfortunately, the water was too shallow for the ship to work, so instead, we used a little barge with feet called the lift boat Myrtle. You can see here, he's got these legs that come down, and they can lower these and raise these. So this barge basically floats out to the site, lowers its feet down on the seafloor, pushes off the bottom, and raises itself up out of the water. Water here is like 15 meters deep, so it was pretty easy to do this. And then I didn't do any of this part work because I'm not a driller, but we welded basically a mining drill rig to the front of the ship, cantilevered a drill floor off the front, and then drilled into the rock and took cores all the way down through the sediments that fill the crater in, and then the sediments that make up the crater is the breccia and melt rocks slid back in right after the asteroid hit, and then the deeper crustal rocks underneath to understand how the crater actually formed. I sailed as a micropaleontologist looking at the fossils that filled it in to understand how life recovered afterwards. Here's a section that we drilled. Here's the peak ring. And we found about 600 meters of post-impact sediments that filled the crater in, 130 meters of impact breccia and melt rock, and then 580 meters of granitic basement that had actually been lifted from about 10 kilometers below the surface, deeper in the crust, to the present position by the asteroid impact. But again, different topic for a talk there. So what we find is, oh no, my did this to me earlier too. Every time I'm in presentation mode with the laser pointer on, if I move the laser pointer weird, PowerPoint doesn't like it and wants to restart. So apologies, let me just restart real quick. But we were looking at the very top of this impact breccia. So, you know, the asteroid hits and the crater forms and all this stuff slides back into the crater right away. There's this whole thing. Let me start this again. This huge sequence of 130 meters of boulders and gravel and all this sediment that piled in. And then after that, everything kind of slows down, and then the tsunami wave comes and churns everything up again. And when all this stuff is finally done and settled, you get this really turbid water column. Everything is all churned up. Share my screen again. All right, sorry about that. Anyway, everything is all churned up, and you get this really turbid water column that very slowly settles out of suspension over the course of a couple of years. And we know it was a couple of years because we find iridium at the top of it. So this is what we call the transitional unit. It's transition from all the breccia that filled in the crater to the, oh, come on, man. Do it to me again. There we go. Can you guys see my laser pointer? Man, come on. Anyway, this is very frustrating. Anyway, so what you can see in this that I would love to point at you, if I was in person, I'd just be gesticulating at the screen with a beer in my hand. But at this lower peak here is some impact debris and soot. But at the top of this level, anyway, at the top of this settling layer, we find iridium, which is atmospheric fallout from the impact. And we know that this atmospheric fallout occurred within a few years of the impact because we've done atmospheric models of all right, you put all this dust in the atmosphere and how long does it take it to settle back down? It's a couple years. And so when we find this stuff, at the top of this layer, then we know that it is within a few years of the impact. All right, third time's the charm, right? Share my screen again. Okay. So anyway, so this level up here at the top of this settling unit has iridium in it, and it is thus something that we know is full of come on. Anyway, who needs slides? Who cares? What we find within the settling unit, we find evidence for life. So this is something that we know was deposited within a couple years of the impact event. And it's got the iridium layer at the top, and then below it, we find burrows from stuff that was burrowing in the sediments, and we find microfossils of survivor species in a very high abundance that we know must have been living in the crater at the time. Put my slides back on, but you don't need. All right, I think I'm still screen sharing, so that's good. Anyway, you can see here evidence. The little yellow circles are showing the burrows. They are not the most beautiful burrows you've ever seen in your life, and they never come up well on my slides, unfortunately. But they are there. I swear that if you go look at these cores, they're nice little tiny little burrows of critters that were living in the crater within a year or two of the impact, even as the sky was dark and the extinction was happening. And we find an increase in survivor species of different groups as well: calcareous nanoplankton, foraminifera, Living within this unit, the settling unit that was deposited a couple years after the impact, we find survivors in the crater. We also find biomarkers for cyanobacteria and bacteria in general, really abundant in this transitional unit, indicating other life that was living in the crater as well that doesn't fossilize, but does leave chemical markers. All of which tells us that the crater was habitable within years of the impact. The crater rim was open to the northeast, which allowed ocean water to flow into the crater, which helped kind of mix things up and kind of equilibrate it with the open ocean, so it wasn't able to get stagnant and isolated. But even at ground zero, even at the place that was, I mean, like literally vaporized when the asteroid hit, the worst impact of the whole in the whole world, the worst environmental change was at ground zero. And even there, life was able to start to recover within a few years, very, very, very quickly, which tells us how ephemeral the environmental changes caused by the asteroid impact were. The sun was blocked out for a few years, which was enough to cause photosynthesis to crash and collapse a bunch of food chains. There were global wildfires, or at least hemispheric wildfires, but also widespread over parts of the world, which would have killed a lot of things on the surface. Probably an increase in acid rain and things like that too. But the main kill mechanism for this extinction was the sun being blocked out for a few years, causing photosynthesis to shut down and causing the food chains to collapse. But that was really quick. Within 4 or 5 years, the sun came back out. Within a few decades or centuries, temperature got back to basically almost normal, like still not quite exactly normal, but well within a livable range for organisms. And yet it was still 10 million years, well after any sort of environmental change was well gone, that biodiversity got back to what it was before. And the reason for this, this was proposed by that paper by Kirchner and Weil in 2000 as something that we tested with our data, that I won't bore you with a bunch of morphometrics and statistics at this time of the evening. But to just kind of summarize, the idea is that basically the ecosystems are extremely complex and ecological interactions are all complex. You probably heard of the term niche space, like an ecological niche, like the thing that an organism does to fit into its ecosystem. It lives on a certain tree or eats a certain type of fish or whatever. We think of niches or niche spaces as something that could be vacated, like a parking spot. The organism dies, the niche space is still there, something you can just slide right back on in and take it. But that's not really how it works. The organisms that occupy a niche, like define that niche. And so if the organism dies, that niche disappears with it. And so what you can think of as extinction doing is as it's killing species, as it's destroying species, it's also destroying ecological niches. And we think about this on a larger scale, we refer to this as ecospace. This absolutely god-awful figure is something I've been trying to find a better version of for the last year and a half. I've given different versions of this talk. This is a visual representation of ecospace in a particular ecosystem. It is just awful barf to look at, but it does very nicely show, visually what this kind of represents. This is a multidimensional space. Each of these dots is a different organism in the ecosystem, and the lines are how these things are connected. You can imagine then, if there was an extinction event, 75% of these dots disappeared, especially the more specialized ones living around the edges have more unique specialized ecospace. They go extinct, they disappear, ecospace in general shrinks. And the time it takes to rebuild that ecospace, to rebuild that ecological complexity, is just a kind of a basic speed limit of diversification, of evolution. And so it doesn't matter what the original environmental change is. When you cause an extinction event, it's going to take 10 million years, a mass extinction event. It's going to take 10 million years for biodiversity to get back to what it was. This looks horrifying, and so I'd like to work through a practical example here. Think about a coral reef, okay? One of the most biodiverse places on Earth. Really, really complex, built out of living organisms, right? Corals are living things that literally build the reef that everything else lives on. There are dozens of species of corals, which are adapted to different parts of the reef. Things that live on the forereef, they live on the top of the reef in the lagoon. You have a huge diversity of fish and invertebrates that have evolved to eat certain kinds of corals, live in certain kinds of corals, eat certain anemones that live on certain kinds of corals, so on and so forth. Again, really complex interactions with very specialized species filling very specific niches throughout the reef. Then you have larger predators coming in, right? Like sharks, which are their own mini ecosystem because they have parasites and they have fish that eat the parasites, so on and so forth. right? So super complex, really diverse ecosystem here. Now imagine there's an extinction event in coral reefs because, I don't know, let's just say the oceans got too hot and the reefs all bleached and died. To pick a totally random example that has no bearing on the real world, right? So if you have this big extinction event, all these things go extinct, you know, it's going to take a long time to rebuild that diversity. It's not like you're just going to like pop back to, oh, and now there's, once again, there's a dozen species of coral and thousands and tens of thousands of species of fish and invertebrates that live there. It's just going to take a long time. And apparently that period of time is about 10 million years. And we know that because we can see that after all the other mass extinction events, and particularly with the Cretaceous, there was no environmental perturbation that lasted more than a few decades or centuries that would have prevented life from just kind of doing its own thing. This was all internal. There was no external pressure holding things back. It was all just internal evolutionary speed limit causing that recovery. So to summarize, there's a long delay in the recovery of diversity after all extinction events, including the one at the end of the Cretaceous. It was caused by an asteroid impact in the Gulf of Mexico. This delay is internal, which means that the time needed to rebuild ecospace is a firm speed limit on diversification after extinction events. Obviously, species that go extinct will never be replaced. You know, the white rhinoceros, the manatee, whatever. When they're gone, they're gone. But biodiversity in general, the number of species that exist on Earth, will be depressed for millions of years if we cause a mass extinction event now. Which means decisions we make now will affect life on Earth for millions of years, which is an extremely sobering thought, but also means we have an opportunity to prevent that. And with that, thank you very much. Happy to answer questions.
Thanks, Chris. And thanks for sticking through all of those technical problems. I appreciate your gesticulating, even though you didn't exactly have a beer in your hand. So next time, you know.
Yeah, next time. Look forward to doing this in person sometime for sure.
Yeah. Oh, man, I can't wait to get back to normal. That was a great talk. We do have a couple questions. So if you're watching and you have a question, please go ahead and continue to drop those into the YouTube comments or Twitters or wherever it is that you are doing this from, and we will pass those along. So you kind of ended on a note that made me think about how astronomy is a weird science because it makes you feel quite insignificant since the universe is very vast and we are a very, very small, very, very small part of it. But in your field, it kind of makes us feel quite significant in what's going to happen and some of the impacts that we have as a species or as a society or whatever on our own world. And so it was just an interesting perspective to get. So I found that to be a little daunting, but one of the questions we have is that these previous recoveries have happened in the absence of species like humans who have had a large impact on the environment, like you mentioned. And do you think that these recovery periods would be different now that humanity has had such an impact on the one that we're going through now?
I think that the impact that humanity is having on the environment, the real difference is one of timing. So when we look at climate change in the past, like the fastest thing that we know of, well, other than the impact of the end of the Cretaceous, which was really quick, years, but the fastest, next fastest change in the past, the warming period at the end of the Paleocene was tens of thousands of years, right? At least at the very fastest, it was a few thousand years of warming and CO2 release, and then like 100,000 years of recovery. So I don't think that humans aren't doing anything or causing anything that's particularly different. It's just that the rate of it is really accelerated. So if we, whenever we stop with the pressure that's causing the extinction, that will cause extinctions to stop, and then life will start to recover. And I don't think it's going to be fundamentally different, whether you're talking about recovery, in 100 years, or when you talk about recovery 100 years after the KPG or whatever. The climate changes, the environmental changes are going to move at their own pace, regardless of what we have been doing. Does that make sense?
Yeah, that does. It's not exactly reassuring.
The thing that should be reassuring is that none of this has happened yet.
True.
Right? So we have time. That's the thing here. It's
not too late.
Not like it's not doom and gloom. There are concrete things that we can do to prevent this from happening. Right? Stop climate change. Stop overfishing. Stop polluting. Stop habitat destruction. These are all things that are easily within our powers as a society. Yes. So it's scary, but it's like we can. It's not preordained.
Yes, true. It is definitely not too late. We have a question about some of those images that you shared. So Alan was wondering if those micrographs are from scanning electron microscopes.
They are indeed.
Okay, cool. And then this was another question that I had. You said something very briefly when you were talking about the digging into the crater and that you found some microfossils that survived. Does that mean that there were species that survived that asteroid impact, or were these things that kind of moved in and evolved or grew afterwards?
Yeah, so when we talk about survivor species, these are species that didn't go extinct.
So
they probably at ground zero, anything that was living there was vaporized, right? Was totally destroyed. Right. But in the ocean around, like there was eventually a certain distance away, things wouldn't have been killed instantly. And then, 75% of all species in the oceans went extinct. 90% of forams went extinct, but a few species survived, and those species were able to come back into the crater, probably basically instantly, because as the water rushed back in, as tsunami brought water back, across the Gulf of Mexico into the crater as well, it would have carried these things in. So it would have been able to colonize the crater very quickly. And it's, I did the math when I was writing this paper, but it's a huge amount of water that fills up this 200-kilometer across crater that's like half a kilometer deep or something, that would very, very quickly take up any residual heat or anything. And the water in the crater would have been the same temperature as the water in the ocean. So
I see. Because it's the same water.
Right, exactly. Because it's connected to the ocean. That's the thing that allows it to recover quickly. So it just brings everything back in, and then it's just kind of back to normal.
That's cool. I was really concerned that there was something that survived that. I was like,
well, not at ground zero, but yeah, a certain distance away, things would have survived.
True.
Including our mammal ancestors.
Well, speaking of some of the big animals that might have survived things, how about the most high profile animal that we've lost to extinction in the last 50 years? I know we're going through an extinction event. What's the most
high profile animal? That is a good question. I don't know. The white rhinoceros is now extinct in the wild, right? It depends on how you define extinct. There's one thing that's still living in a zoo or whatever. I couldn't pick a single thing that sticks out. The thing is, it's not the one really charismatic thing. It's the overall effect on ecosystems. That a lot of less charismatic, less exciting animals put in the work day in and day out to actually make ecosystems work the way that they do. So it's not just like the vaquita or pangolins or white rhinoceros or whatever.
Yeah. Awesome. Well, thank you for that very slightly terrifying presentation. And we're going to go ahead and close the show. And so if you guys have more questions for our speakers or for the news, please continue to drop those in and we'll call them back after we do our closing. So Chris, thank you very much. That was a great talk. Micaela, if you would like to come back.
Hello.
All right.
Well, okay, great. Thank you for joining us for this month's AoTATX show. Please play our trivia game. It's short and sweet, and that increases your chances of getting a winning slot in our prize category. We will keep the trivia game live for anybody who's watching this show, tomorrow or the next couple of days. We will close the trivia game sort of end of day Friday. So you have until Friday to play. And once the game is over, we will post the answers to our website. So aotatx.org/trivia. And then you can find there the answers to all of our recent trivia questions and games. So check that out.
Also, just check out the really cool website that Micaela made because she did a really good job. Again, we're going to give a big thanks to the North Door for being our host for so many years. Thoughts go out to them and all the people who worked there. Thank you for making it such a memorable experience and for making one of our shows one of the best, I think, in the world. Another thank you to tonight's speakers. You guys did a great job. To our news people for coming in last minute for us. To all of our space cadets and everybody else who does this astronomy show that is not here on camera. There are a lot of people behind the scenes that make this happen every month. We couldn't do it without you guys, and so thank you. Shout out to people moderating the comments and passing us questions, because doing too many things at once is overwhelming. And of course, most of all, thank you to you guys for watching the show. You are the reason that we keep going. This is our 73rd show in a row. Every month we've been doing this for the past 73 months, and it's because you guys keep coming back and you keep encouraging us. I learned a lot of things, and I'm really happy that we get to provide this kind of opportunity, even especially given the current circumstances.
I was going to say related to that, but I think I'm going out of order here. But related to Rebecca's comment about 73 uninterrupted months, I just wanted to re-emphasize how incredible that is. I feel like I've been really lucky to have been a host of this show for the last, I actually don't know how many months, but some. And
number of what is time?
Like, you know, like a handful, but this show just has such a rich history of years and years of amazing speakers, amazing, you know, space cadets, and awesome talks. And at some point in the future, we will be back in person together.
Yeah. And if you'd like to watch any of the things that we've done before, you can connect with us and watch our YouTube channel. All of our talks are there. We are working on reorganizing things so it's a little bit easier for you to find things by subject matter and all of that. And when we find time to do that, we will be doing it. So in the meantime, you can search our channel for any kind of thing about astronomy related science that might be interesting to you. You can connect with us on Facebook. We have a page and a group. We're on Twitter, of course, and Instagram. And so if you have any questions for us, you can post any of them there, or you can send us an email. If there's a topic that you really, really want to hear about, let us know. We have a sign up thing on our website to sign up for our newsletter, so you get a notification every month that we're doing a show and what it's about. So you can find that on our website at AoTATX.org. And then, of course, like I said, Astronomy on Tap is a global event enterprise, and we are just one of many, almost over 30 or 40 different locations that do Astronomy on Tap every month. So if you're not in Austin and you're watching this from somewhere else, check it out, see if there's one in your city. There's plenty of them doing online virtual events right now, so go ahead on the astronomyontap.org website and check those out.
And while you're on our YouTube channel, don't forget to check out our show last month with English subtitles.
Yes. All right, so that is all we have for our show, but we do have some more questions. So if we could call back all of our speakers and our news people, we want to get through all of your questions while we still have time. Hello, everyone. And Jackie's not here to make a talking heads joke, so I feel like insert talking heads joke now. Check done. So I guess we can start off with a question for Kirk. So has there been any kind of collaboration between the radar sounders and the surface rovers in the case of like the Earth's moon or Mars?
Yeah, there definitely has been. Something I had in my talk, but I cut due to time, is you can use the spaceborne radar sounders to look at the roughness of the surface. So Schirra data has actually been used in landing site selection for, I think it was Curiosity, and it's definitely been used by somebody at UTIG for Mars 2020 Perseverance. So, and InSight as well. So where they chose those landing spots was partially informed by data from the radar sounders. So there definitely is cross instrument, cross mission science that's going on between the spaceborne sounders and the rovers.
That's really cool. I really appreciate that. I like it when all of the sciences work together, because I mean, we couldn't do anything without knowing anything about geology if we were trying to study a moon or a planet. So it's very exciting to see collaborations like that. Micaela, is there other question?
Yeah, I have another question for Kirk from Pete. Hi, Pete. How effectively does radar sounding distinguish between ice and rock? And can we assume that radar sounding is critical to finding water and therefore life on other planets?
Well, what's really interesting is how radar waves move through ice and rock and water is very different. And it's those reflection characteristics that change in the material properties of ice, rock, and water at that interface leads to different reflections. So if I was going from ice to, we'll take the case of Europa, ice to water, like that at the bottom ice ocean interface, that's going to be a very, very bright reflection because there's a very strong contrast in the material properties at that interface. So there might even be chances that it's stronger than the surface reflection. So the brightest thing we see might be something 30 kilometers in the base of the ice shelf, just because that contrast is so large. And then ice to rock is a little bit more subtle. Like you saw when we were looking at the Sherrod data, that air ice reflection was almost as strong as that ice rock reflection. That's because the change in material properties at those two interfaces is very similar. So, yes.
Cool. That's really cool. That like you can, something that's that much deeper can be that much brighter. That's crazy.
Oh, very much so.
Sweet. Okay, I have, let's see, a question. Sorry, we collect questions from a number of places here. I have a question for Chris, and that is, you described what happens to a crater that is in or near the ocean. How is that different for one that's completely landlocked?
Basically, the water doesn't come back into it right away. So we have an asteroid impact that just happens on land. You still get the ground flow of all the stuff coming back into the crater. So the asteroid hits and stuff comes out, and then a bunch of stuff comes sloshing back in, basically, or sliding back into the crater as the crater forms. In the ocean, you get water coming with it that brings a lot of stuff too. But on land, it's just a kind of like rock fall coming back into the crater. And then, like eventually it'll form a lake because it's probably below the water table. But yeah, it's just a dry process where just a bunch of rocks fall back in.
Does that slow the process of species moving back into the area at all, or not?
It can, yeah. It depends on what the kind of the rock is. The analogy there would be like a volcanic eruption where you get fresh lava that doesn't have any nutrients in the, for like nitrogen or anything that's been fixed that plants can use. So it takes a long time to kind of establish life. An interesting comparison in a marine crater actually is the Chesapeake Bay impact structure, which is a smaller crater in the Chesapeake Bay, as you might expect, in Virginia and Delaware, North Carolina. It's about 50 kilometers across. But because it wasn't open on any side, it was just basically closed all the way through. It formed basically a bowl. And you get a layer within the crater that was poorly mixed, and so it didn't have any oxygen in the water. And so actually in the crater, even the smaller crater from an asteroid impact that didn't cause any extinction event, it took life like 10,000 years to start to colonize inside the crater, just because of the structure, the shape of the crater. There wasn't any oxygen in this deep bowl for anything to live. So.
Wow, okay, that's really cool.
So kind of along those same lines, I have a question that ties the two talks together. So what can studying like this impact crater tell us about the potential for life in other planets and moons in the solar system? So how can what you do help us learn more about what Kirk does?
Excellent question. This is something that when I give the hour-long version of this talk, I usually include a couple slides for, but yeah, I mean, I could talk like all night about all the cool little side stuff with this, but yeah, so Chicxulub is the only peak ring crater on Earth. So craters over a certain size have an interior ring, like a discontinuous set of hills. Schrödinger crater on the moon is a good example of one. We see these in rocky bodies across the solar system. And when we look at them, there are some different hypotheses about how they formed, competing hypotheses, actually. There's one that was based on bomb codes from like atom bomb tests. They could use the energy that was released by the atom bombs to actually make some inferences about cratering processes. And there was another set of assumptions that was based on just observing craters on the moon. And these produced two different hypotheses about how peak rings and craters form. When we went out and drilled Chicxulub, we were able to test them. To summarize things really briefly, basically one hypothesis predicted that the peak ring would be made out of shallow crustal rocks like limestones or something. Something from the shallow crust, which in that area would be limestone. And then the other model predicted to be something from deeper in the crust, some sort of crystalline rock like granite or schist or whatever. So basically to test this hypothesis, we just had to go out and drill a hole in the ground and see what kind of rock was at the bottom of the hole that made up the peak ring. And it was granite, which, proved one of the hypotheses correct. But this is important because it then tells us about what the subsurface structure of these craters are. How do the hydrothermal systems form? If there's water present in the crust, things like that. On early Earth, one of the hypotheses for how life actually evolved on Earth was that it was in hydrothermal systems associated with large impact craters. That might have been a place where you have heat and you have fluid flow and you have a lot of the chemicals necessary for life. And that could be the same case on other rocky bodies, on other planets and moons across the solar system and the galaxy, right? And so understanding how these cratering processes work are kind of like a fundamental question of rocky planets everywhere. And if you want to study it, you can either go to Chicxulub or you can go to the moon, the next closest one. So yeah, it was really exciting for like a dozen different reasons. It was a really successful expedition. We were all really excited about it.
Changing gears slightly, I think we have a question for the news. I think, Sam, you were doing the story about water on Mars, and the question was, wouldn't the extreme pressure keep the lake in liquid form?
Yeah, so I actually did a little bit of Googling because I saw that question. It turns out it would help a little bit. I'm not sure what kinds of pressures are underneath those sorts of very thick ice caps at the polar ice caps of Mars. But the phase diagram of water between liquid and solid is pretty much vertical. There's a little dip at around 1,000 atmospheres that gives you like 25 degrees Celsius colder transition between liquid and solid. But so it helps a little bit, but not enough. So yeah, the two hypotheses are it's very salty or there's some sort of other heating going on from the underside from the planet itself. So yeah, the pressure helps a little bit, but not enough.
Okay, cool, nice. I think we have a question that I probably will open up here because I love it when our audience gives us questions that we can ask everybody. Jeff is asking when we wipe ourselves out. So we'll just after that. What's your bet? What's your bet on the next species to evolve intelligence?
Does it have to be biological? Because I am all for robot overlords. Like can we just Terminator that?
Yeah, I was gonna guess.
Is that really evolution?
Like dolphins or something. They're pretty smart, right?
Octopus are pretty smart.
Octopus too? Yeah.
Oh, come on, guys.
I'm going to say some sort of squirrel, maybe porcupine.
What?
Our ancestors came out of forests, right? And there was a lot of climate change that caused like forest to retreat and grasslands to grow, and then forests came back, and all this back and forth that kind of forced them to evolve in a way that developed like bipedalism and then eating meat and all that stuff. So I'm going to put my money on a forest dweller. So I think squirrels, maybe porcupines, something along those lines.
That'd be a shock.
I like it.
The squirrels at UT are definitely smart enough to know who feeds them and who doesn't. That's for sure. Okay, we have another question. So other than the KPG extinction, are there other extinction events that might be pertinent to understanding modern climate change?
Yes. So there aren't. So KPG is the most recent major mass extinction. The two before that were caused by huge volcanism periods. So that the Permian or the Permian Triassic mass extinction was caused by eruption of the Siberian traps. The Jurassic-Triassic mass extinction was caused by the Central Atlantic magmatic province from the opening of the Atlantic Ocean. But there are smaller extinction events that aren't like, 75% of life went extinct, but big climate change occurred and some certain organisms went extinct. So there's a lot of extinction that occurred in the oceans 55 million years ago when there's a gigantic release of carbon, either from volcanism or from permafrost and methane in the seafloor, or maybe a combination thereof, volcanism and methane release. But it caused a bunch of CO2 to be released, which caused a major ocean acidification event, which caused a big extinction of corals, reefs, coralline algae, things like that, and organisms in the oceans that live deep in the ocean. About 15 million years later, there was a big extinction event that was associated with the development of the first ice sheets on Antarctica, which caused big reorganization of ocean circulation and obviously major cooling, because that's how you get major ice sheets. And so you had a lot of things that had evolved and had evolutionary lineages going back like 100 million years in a period of Earth history that had no ice sheets and was always really warm. And then these things all went extinct, and then you have new things that have evolved that have evolutionary histories that are surviving in colder periods of time. And so then what happens in the future when if things get really bad and we destroy all the ice sheets, we go back, we flip back into a warm climate, what happens there, right? Those are kind of interesting ways to try to understand the biosphere and the response of life to different climate changes as well. So yeah, the short answer to the question is yes, definitely. Like whenever there's a climate change in Earth history, we can look at how life responded to it and the organisms that did well and the organisms that went extinct to understand just generally how does life respond to those kinds of changes. That's why it's important to study the Earth's history in general, because it gives you these perspectives on things that you don't get from looking at human observations of the biosphere for the last 300 years or whatever.
Yes, it's important to know on a larger scale, like how things, which is like our whole deal, how on a larger scale.
I think excuse me, I think I've got one final question for Kirk. Back to Europa, what would be the number one thing you hope to find and learn?
One thing I hope to find and learn. Just so many.
You can have more than one.
I am a big fan of, I'm really excited to look for plumes with the radar, because I think that is just the audacity to do that is just so weird. It's not a way anybody would ever think to look for a plume. We have dust analyzers, spectrometers on Europa Clipper that you fly through the plume. They can collect anything, measure it, and look at the spectrograph and figure out what's there. But to do that with the radar, where we don't have to fly through the plume, we just have to fly maybe over it. I think that's just, I think it's going to be really exciting, and I think it's going to be a lot of unexpected results, I hope. That's what I'm excited for on the plumes.
Nice, very cool. Looking forward to it.
Maybe in a decade or so.
Astronomy is we are also very familiar with the flagship style missions. The one that comes forefront to mind, which I have to bring up because nobody has yet, is of course JWST, Rebecca. Anyway, on that note.
We're not going to talk about that.
Thank you, everybody, for joining us. Thank you again to the speakers and to Sam and Oscar for doing the news. And thank you for joining us for this show.
Yes, thanks, everyone. Have a great night. We will be back next month for another show. So sign up for our newsletter, subscribe to the channel, do all of the things so you can be notified when that happens. Thank you, everyone.
Good night.